this chapter, we will be introducing and studying derivatives. In this lesson, we're going to talk specifically about the derivative, its notation, and some of its properties.
All right, everybody, we're going to start to talk about derivatives. Now we're really getting into what calculus is. And in fact, the majority of the rest of this course is going to be about this one idea. Okay, we're going to look at applications and then doing derivatives of different types of functions. This is really one of those really big ideas. And in fact, if you've ever used that expression, to tell somebody that, what you're working on isn't all that complicated, you might have said at one point, well, it's not rocket science. Well, this kind of is starting to look like rocket science, okay? This, when we start talking about calculus, this is the kind of math that you're doing. Now, it's not exactly, you don't go to NASA and they're not just doing a bunch of calculus. They're doing a lot more really complicated math there, but this is certainly pointing in that direction. So the derivative of a function f at some number a is this right here. Now, I want you to notice the little bit of the notation here. Notice that we use this little apostrophe right there. We call that f primed. And when you see that little apostrophe right there, that means the derivative of the function. And when we plug the value a in here, that means we're plugging in some sort of specific number in for the independent variable. Now, that is right here. That is the limit as h approaches 0 of this function right here. And this is f evaluated at a plus h minus f of a all over h. This is y minus y, and then remember h was the difference between them. We called this first principles, okay? First principles. Without the limit, this is called Newton's quotient, which is really just the slope, okay? The slope of a secant line. But as soon as you throw the limit as h approaches 0 in front of that, that becomes the slope of the tangent. Another way of writing this, and it looks a lot more like the slope expression there that you would have learned earlier, is this right here. The limit as x approaches a, okay, of f of x minus f of a over x minus a. And here you can clearly see those 2 points, x comma f of x, a comma f of a, y minus y over x minus x. There's your slope. So remember that the derivative is the slope of the tangent line to a specific function. Okay, slope of the tangent line at that specific point. Now, this right here, this is, well, both of these, the way they're written right now, are both very specific to finding it at a specific point where x is equal to a. Okay, we give some sort of special value to x. We're looking at it right here at a. But you can actually do it a little bit more generally than that. Okay, you can have a little bit more of a general approach and use this to find or to create an expression for the slope of the tangent line to the curve, basically at any given point. And we do that simply by using first principles, but instead of using a in there, that specific number, we're just going to use x, okay, the independent variable. So this right here, again, f primed, remember that apostrophe there means derivative. So the derivative of a function is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h, y minus y over h. And then the difference being here that the x values here are just offset by this value h here. And we're going to let that little value h there approach 0. Now, don't lose your connection to this next statement here, okay? This next little bit right here, that a derivative represents a rate of change. Okay, it is a slope. This is all we're doing. Sometimes the math can get a little complicated, can get a little bogged down in algebra, okay? And in fact, it's often the case that you're working through a problem. Your very first step is a very simple, straightforward calculus step. And then you've got like half a page of work that's all just algebra trying to rearrange and simplify. While you're kind of slogging your way through this, don't lose sight of the fact that all we're doing here is looking at the slope of the tangent line. We're looking at a rate of change, okay? That's all it is. Looking for the rate of change of a function. Now, what we're doing right here is just showing you the different ways that you might write this, okay? So the limit as delta x approaches 0 of delta y over delta x, remember this is just your slope. So what we're saying right here is that when you take your slope and allow that change in x to approach 0, then what happens here is this is when you create the derivative. Okay, so remember, this is delta. These are for macroscopic steps. Delta x means I've got, here's my x, I take a jump, here's my next x. And then delta y, here's my y, and take a big jump, there's my other y there. That's the difference between them, is big. When I take these steps right here and make them very, very small, we replace the delta with the letter d. dy by dx, still a slope. Change in y over change in x, little change in y over a little change in x. Okay, so here's your derivative, and this is what we would call Leibniz notation. Now, we're lazy though, so we use f primed or y primed. Okay, these are the two probably most common around where I live. These are the most common ways we represent that. Over here though, you might see people write this big D for the derivative of f of x. Big D, the little subscript x here is basically just identifying what the independent variable is. So this is the derivative of y, and we're just stating that the independent variable is x. This dx down here, it is important, particularly if you're starting to play with the variables, you're using different variables, maybe you're using more variables because of whatever problem you're working with. It's often really useful to use this notation because it identifies what the independent variable is. Like in most cases, when we write these guys right here, we're assuming that the independent variable is x. Okay, sometimes it's harder to tell, so this notation becomes a little bit more useful. I don't want to make a huge deal out of that right now at this point in time because it's not a big deal. Okay, just bear in mind that these are the ones you're probably most often going to use. You very infrequently would see these. And the useful part of this right here is that it does identify that the independent variable is x. If you want to evaluate the derivative of a given value of x, and let's say you're given it at a, then sometimes you might write it like this. Okay, dy by dx, or f primed of x, square bracket, and then this little subscript down here, x equals a. Okay, or use the straight up and down line there. Sometimes you'll see that x equals a, or just f primed at a. And we've already seen that earlier in this lesson. Now, graphically, the derivative represents the slope of the tangent line at a point of tangency to the curve. Okay, but it can be used in any context where it might consider how one variable changes with respect to another. And this is a lot of what you're going to see in this course. Is we're going to explore some of the applications of this idea. In fact, you might be shocked at just how useful it is to know what the slope of the tangent line at a specific point is. Okay, you're going to see this pop up all over the place, from business to biology to physics. It's just everywhere. Now, ultimately, calculus is the mathematics of change. Okay, prior to this point here, your mathematics is very static. Okay, when you measure the height of a building with its shadow, you're assuming the shadow for that little bit of time that you're measuring it is staying still. It's not moving anywhere. You make your measurements, you come up with your calculation, boom, there it is. Calculus is about how changing one variable causes a change in another. So one really clear application is velocity, okay, which is the rate of change of distance with respect to time. In fact, this is going to be one of the first applications we look at. And you will see, for those of you that have taken physics or even just science classes in high school, you'll see how this would directly apply to the stuff that you would have studied in those classes right there. Okay, so like I said, we will spend a little bit more time on that later. For right now, let's take a look at just some examples of finding the derivative. Okay, everybody, so for our first example here, given that f of x is equal to 3x squared plus 4x plus 1, we're going to find the derivative. Okay, we're going to find the slope of the tangent when x is equal to 2. So at that specific point here, okay? Now, because we're finding it at a very specific point here, I think what we'll do to start off with, now this isn't how this is going to play out every time we do these questions, but for this first time here, what I'm going to do here is I'm going to use this expression. We're going to take the limit as x approaches a, in this case 2, and that is going to be f of x minus f of 2 all over x minus 2. Okay, so the limit as x approaches 2. And the reason I'm using this one here is because I have this specific point that I'm evaluating. And we saw in a previous example, in a previous lesson, that to use first principles, when we have this very specific number, the first principles is a little bit longer to use here. So now, let's just take this out and take a look at this formula here. F of x is 3x squared plus 4x plus 1 minus, okay, now f of 2. F of 2, well, that's just the function evaluated at 2. So 2 squared is 4 times 3 is 12. 2 times 4 is 8. So 12 plus 8 is 20, plus 1 is 21. So this is going to be minus 21 all over x minus 2. Okay, so let's see where this goes here. So this is now the limit as x approaches 2 of 3x squared plus 4x. Now I've got plus 1 minus 21. So it's going to be minus 20 all over x minus 2. All right, well, now I'm looking at the limit of a rational expression here. Experience tells me that I probably have to factor this. Now, experience also gives me a little bit of more information here. I also know that if I'm going to get an actual limit here, that's probably because one of the factors here is x minus 2. So I can kind of anticipate where this is going. Now, if that's the case, then up in my numerator here, to get the 3x squared in the previous step, this has to be a 3x. And to get the final product here to be minus 20 at the end here, this has to be plus 10. Now, does that actually work? Let's multiply this numerator out here. Let's multiply these binomials out here. X times 3x, okay, is going to be 3x squared. X times 10 will be positive 10x. Negative 2 times 3 is going to be negative 6. Negative 2 times 10 is negative 20. And now notice that negative 10x minus 6x is positive 4x. So that actually works out great. That's wonderful. So that is the way that is supposed to factor. I know that my x minus 2 divided by my x minus 2 will become a 1. So those will cancel. Now that's only true if x doesn't equal 2. Remember, but I never get to 2. I'm taking the limit as x approaches 2. So by definition, I never actually get to 2. Now, though, I can plug in 2 into what's left here. 3 times x plus 10. So 3 times 2 plus 10. That's going to be 16. Okay, so the slope of the tangent line at the point, okay, and I might even say it like this. The slope of the tangent line to f of x equal 3x squared plus 4x plus 1 at the point, and now I actually know the whole point here. I know it's going to be the point 2 comma 21. I figured that out. Is 16. Okay, and there you go. Okay, everyone, we're going to take a look at this question again, but this time I'm going to use first principles to get to my answer here. Okay, so to start off with, we're going to figure out what the derivative is. And I'm going to use this notation right here, dy by dx. And we know that this is the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, now we got to jump into this here. So this is the limit as h approaches 0. Now f of x plus h, remember what our original function is. It's 3x squared plus 4x plus 1. So this is going to be 3, but this time it'll be x plus h squared plus 4 times x plus h plus 1. Now those three terms there, that is just the f of x plus h. Now I'm going to subtract from that. I'm going to put this in parentheses. F of x, which is 3x squared plus 4x plus 1. Oops, plus 1. This will all be over h. All right, now that's kind of big and ugly here. It's going to get a little bigger and a little uglier in a second because I'm going to now expand out this first term, this 3 times x plus h squared. That will end up becoming 3x squared plus. Now, when I expand out x plus h squared, the middle term will be 2xh. And when I multiply by 3, I'm going to get 6xh plus h squared multiplied by 3, so 3h squared. Then I'm on to my second term, the 4 multiplied by x plus h, and that will be 4x plus 4h plus 1. And now I'm going to distribute that negative through, so minus 3x squared minus 4x minus 1. Okay, all over h. Wow, we got a lot going on up there. This is actually going to simplify down rather nicely, though. Okay, the 3x squared minus 3x squared goes away. 4x minus 4x goes away. Positive 1 minus 1 goes away. And now notice every term that I'm left with in the numerator here has got an h in it. Well, I'm dividing by h. So when I do that, I'm going to get some canceling here. And this is going to end up being the limit as h approaches 0 of 6x. I can see what letter I wrote there. 6x plus 3h plus 4. And now when I take the limit of this expression by letting h go to 0, okay, that middle term is going to disappear, and I'm left with 6x plus 4. So this expression right here is the derivative of f of x, okay, the original function here. So this is, therefore, I can write this in a slightly different notation. I have dy by dx at the top there, but I can also write that as f primed of x is going to equal 6x plus 4. And now, therefore, over here, if I want to evaluate the derivative at 2, I will simply plug that in. Okay, 6 times 2 is 12, plus 4 is 16, which is just exactly what we got when we did it using the other method. I just wanted you to see how first principles would work there. All right, everybody, in this case, the question is saying if f of x is equal to the square root of 2x, then we want to find the derivative of f of x. Now, notice I'm leaving an x in there in place of the independent variable. Okay, so we don't actually have a specific point that we're trying to find the derivative at. It's kind of this general expression. So you can see this right away here. I'm going to end up with an expression for the slope that can be applied to any particular point along this curve. Now, that method that I used in the previous question won't actually work here because I don't have a specific number, or at least it doesn't work in the same way. I could throw variables in there and make the variables work. It's actually a lot cleaner if we actually just do this. If we take and set the derivative, not set the derivative, we use first principles to find the derivative, because this is actually exactly the sort of problem that first principles is really designed to address here. So now this will become the limit as h approaches 0. Now f of x plus h, remember that what we're doing here in that notation is we're replacing the independent variable in the function with x plus h. So in the original function here, what we're doing is we're taking the independent variable, multiplying it by 2, and then square rooting the result. Now, the independent variable is x. Now, in this case, I want the independent variable to be x plus h. So this is going to be 2 multiplied by x plus h. Now, if you write it the way I just did that here, it's wrong, okay? Because the independent variable is now x plus h, but all I multiplied by 2 was the x. I must put parentheses around that, or else I've done that incorrectly, okay? Which is why I said in an earlier lesson that it becomes very, very clear if you understand function notation as soon as you start to use the first principles formula here. Now, this is still the square root, and then we're going to subtract the square root of 2x. So notice that the function shows up twice in the first principles equation here. This is all over h. Okay. So now I'm taking the limit of a rational expression, but notice that I've got these radicals in there. If you think back to our chapter on limits, the way I dealt with that was to use the binomial conjugate. So I'm going to have to multiply numerator and denominator by this right here. Now I'm using the binomial conjugate of the numerator. Now, please make sure you write a numerator and a denominator here. I've had all sorts of students that only ever wrote the 1 and with the idea being that that got distributed to the numerator and denominator, and that is just not true. That is not the way multiplication works. So although their intention is correct, the way they wrote it was very incorrect, and it's hard to mark that. It's hard to look at that because it's written so poorly. Okay, it really makes it look like there's a deep misunderstanding of the way fractions work when you write it out like that. You must write the numerator and the denominator separately for that to make it clear that you understand what you're doing. So now when you multiply those together, you think back to the work that you would have done ages ago on these radicals here and binomials with radicals. This is going to get us 2x plus h minus 2x in the numerator. Now the denominator here, I've still got that h there, and then I've got the square root of 2x plus h plus the square root of 2x. Okay, I'm not going to do anything with the denominator because I already have a sense of that something's going to cancel here. This is going to end up being the limit as h approaches 0. In my numerator, I get 2x plus 2h minus 2x. I like how that's looking. All over h. Then this becomes the root of 2x plus h minus the root of 2x. Now, in the numerator, this is wonderful because what happens here is the 2x's go away. Then I'm left with just a 2h in the numerator over an h in the denominator, and then the h's go away. And again, I can cancel those because I never actually get to 0. I only ever approach 0. So now in my last step here, I can take the limit, I can substitute in the 0 in for this h right here in the expression. And so what I'm left with is 1 over root 2x. Oh, I'm sorry, this should have been a plus. I'm sorry, that was a plus right from the way up here. In the denominator, I get 1 over root 2x plus root 2x. Oh, I'm sorry, 2. Wow. Did a couple goofy things here. Hold on. A couple goofy things. In the numerator there, sorry, that's not a 1. The 2's don't cancel. There's a 2 up there. And then you're left with 2 over 2 square root of 2x. And now those 2's are going to cancel. And what we're left with here is the derivative is equal to 1 over the square root of 2x. Okay. Now, what's really neat about this is that this is an expression that gives you all of the possible tangent line slopes all along this original curve. That's just amazing to me that we've got an expression that'll do that. So if you want the slope when x is equal to 3, you just plug in 3 into this, and it'll give you the slope of the tangent line to the original curve. That's amazing.
Now we'll look at some of the specific properties of the derivative.
Okay, everybody. So note that the derivative, now this should not say of, sorry about that. This should not say of f prime of x. Note that the derivative f prime of x of the function f of x is also a function, okay? So that's going to be a rule that you're going to see here. When you take the derivative of a function, the result that you're going to get is also going to be a function. In addition, notice that the degree of the function always decreases by 1 when we take the derivative. Now, if you didn't quite notice that, let me go back and review this for you here real quick. I'll show you what I mean. So when we took the derivative here of 3x squared plus 4x plus 1, now, that wasn't quite so clear the first time we did it, but the second time that we did this, I used first principles, and we got that the derivative was 6x plus 4. Notice that the original was a quadratic. The derivative is linear, okay? That the degree of that function dropped by 1. Now, over here in the second example that we did, when we took the derivative of this one, we ended up getting 1 over the square root of 2x here. Now, remember that the degree is the exponent of the variable here. So in this case right here, the degree is going to be 1/2. But down here, the degree of this expression is going to end up being negative 1/2. And so again, we see a drop of 1. A drop of 1 here, a drop of 1 right there. So that's significant, okay? Now, additionally, another thing that I want you to notice here is we want to take a quick look at the relationship here between the domain and range of the function and its derivative. So when we take a look at for example, the square root of 2x, notice that the domain is going to be that x is greater than or equal to 0, and then the range is going to be also greater than or equal to 0. Now, the range really isn't the issue here. The issue that I want to draw your attention to is the domain. When we take the derivative, we got 1 over the square root of 2x. Notice now that the domain is x has got to be greater than 0. And then correspondingly, the range here is going to be y is greater than 0. But notice that the domain is now smaller than the domain of the original. That is not always going to be the case. In a lot of the questions that you'll do here, when you use first principles to get a function for the derivative, the domain of the derivative will be the same as the domain of the original. Okay, that happens quite a bit here. But when it does change, the domain of the derivative is going to be smaller than the domain of the original. Okay, we're going to lose something. So in this case, we had 0 was part of the domain of the original function. When there's a change, it's going to get smaller. Now all of a sudden we've lost the 0. Now that's not a huge difference in the domain, but it is significant. Okay, that happens here. The domain, because we're talking about the slope of the tangent line to any point on the curve here, bear in mind that the domain of the derivative cannot get larger. You can't have a derivative defined where the original function isn't defined. You can't talk about the slope of the tangent to a function if there is no function. That's why this has to get smaller here. Now, notice we lost the 0 here. That's because something interesting is happening at the 0. We'll talk about that in a later course here. Okay, it's just the 0 that we lost. That's kind of interesting here. Now, but the fact that the domain here is excluding negatives here, and so in our the domain of the derivative, we're also excluding negatives. That is significant. That is a fact that I want you to be really, really cognizant of. So the domain and the range of the derivative are not necessarily the same as the domain and range of the original function. Just bear in mind that the domain of the derivative will technically be a subset of the domain of the original function. It's got to get smaller, not larger. It cannot be defined in places where the original function is not defined. Near the very end of this course, this issue is going to come back up again. We're going to have a little bit of chat again about how that works.
Now we'll consider what it means to be a differentiable function.
Okay, now before we go on and finish up what this lesson is all about here, there's a couple more examples we're going to do here. I want to talk very, very quickly about differentiable functions. Okay, so we're talking about finding the derivative. Okay, another word for this process is differentiating. So finding the derivative is also called differentiating. A function is differentiable. Okay, a function is differentiable at some value x, like 1 here, for example. Oh, sorry, this should have been an a. That would have made more sense here. So f function is differentiable at x equals a if, now this is not a misspelling of the word if. When you've got two f's there, that means if and only if the derivative of f at a exists. So in other words, as long as you can find the derivative of the function at a specific value, then it is considered differentiable. Now, the reason I bring this up here is because it's not always true that a function is differentiable. It is not always possible to find the derivative of a function, even if the function actually exists. And this is what we want to, I want to show you an example of this right now. So consider the graph of the function here. Consider the function, the absolute value of x. We're going to show that it's not differentiable at x equals 0. Now, f at 0, okay, if I plug 0 into this, I take the absolute value of 0. My answer is 0. The original function does exist there, okay? It does exist, but you can't take the derivative of it there. And we want to talk about what's going on there. So bear in mind a couple of things. Bear in mind, first of all, what an absolute value looks like, and we'll talk about that in just a second here. But also bear in mind, okay, that the derivative is the slope of the tangent line. You always want to go back to that. That's your anchor as we go through this material here. So now let's take a little bit more of a closer look at this specific example. Okay, so to show that the function, the absolute value of x, is not differentiable at x equals 0, I'm going to take kind of a very direct route to it. What I'm going to do here is I'm going to use the first principles here, but I'm going to use the first principles, the very first example that we see in this lesson where we have the specific value in there. So we're going to take the limit as h approaches 0, but I'm going to make this is going to be f of a plus h minus f of a all over h. So basically, I already know that I'm going to take, I'm looking for the derivative when x is equal to 0. So I'm going to plug that in for a right away. I don't need to come up with the general expression for this first. I can do this very, very directly. So this will be f of 0 plus h minus f of 0 all over h. Okay. And so now this is the limit as h approaches 0. This will be the absolute value of 0 plus h minus the absolute value of 0 all over h. So this is going to end up being the limit as h approaches 0 of, now the absolute value of 0 is just going to be 0, and 0 plus h is just h. So this is just the absolute value of h over h. Okay. Now, to determine the limit at this point, what I got to do is I actually have to break apart the absolute value there into a piecewise function. So this is going to be the limit as h approaches 0. This is going to be h over h, positive h over h, as long as h is greater than 0. And it'll end up being negative h over h so long as h is less than 0. Now notice that I can't actually include 0 in this. That's why I don't include it in the domain in either one of those. And the reason for that is because the function is undefined at 0. So I can't include it. So now this is going to be equal to, okay, the limit as h approaches 0. And that first expression is going to be 1, simplified down to 1, as long as h is greater than 0. And it's going to simplify down to negative 1, so long as h is less than 0. Now, for a limit to exist, I should be able to approach it from both directions and get the same result. But in this case here, okay, note that if you take the limit as h approaches 0 from the right, okay, in this particular function here, I'll just say f of, actually, I'll clean that up. I'll write that down there exactly the way we've got it there. Of 1 where h is greater than 0, negative 1 where h is less than 0, that this is going to end up being positive 1. Because when I approach h from the positive side, that's here. However, if you take the limit as h approaches 0 from the negative side of 1 if h is greater than 0, negative 1 if h is less than 0, the answer here is going to be negative 1, because in this case, this is the domain that applies, and the results are not the same. So therefore, the limit as h approaches 0, okay, of the absolute value of h over h does not exist. Therefore, the derivative of this function here does not exist. This function is not differentiable at that point. I cannot take the derivative of it. Now, that actually makes a lot of sense. And the reason it makes a lot of sense here is because if you graph this, notice that if we draw y equals the absolute value of x there, the graph looks like this. At 0, we've got a sharp point. Okay, well, not a sharp point, but a corner. Okay, now, how do you draw a tangent line to a corner? Does it look like that? Does it look like that? Does it look like that? Like, how do you orient it on a corner? Think about putting a meter stick against the corner of a wall. Where do you align the meter stick so that it runs tangent to the wall? Well, the question is, I don't know. Okay, there is no definable tangent line to a corner like that. And this is just one example of an issue that occurs, okay? So right here, we've got a corner. Can't draw a tangent line to a corner. Another example, if you want another one, is something that we call a cusp. And if you've got a graph that does something like this, where it's got this little sharp point, it might even look like this, where it drops down like this, and we'll see examples of this. This is also a place right there where you cannot draw a tangent line, and this is because this is a sharp point on the graph. But there is, as a result, no definable way to draw a tangent line at that point there. So here are a couple of examples of functions that have points on them that are not differentiable. These functions are not differentiable at these particular values. The absolute value is just a really good one to start off with because you've already seen this function, you're familiar with it, and it's easy to demonstrate that there's a problem there.
To conclude this lesson, I want to help illustrate the properties of the derivative a little bit more clearly by showing you what the derivative of a function would look like if you sketched it. These will just be rough sketches.
Okay, everybody. Now, just to kind of wrap up this lesson here, we're going to take a look at how you sketch the derivative of a given function here. So let's say, just for argument's sake, that we've got a graph here, and let's say that it's a quadratic, something like this. Okay, so now I'm going to change colors here. I'm going to sketch the derivative of this in red. What I want you to notice here or remember is that a derivative is the slope of the tangent. Okay, the slope of the tangent line. So right now we're looking at this. We're going to sketch the slope of the tangent. And the second thing that I need you to remember here is that there was a drop of degree. Okay, when we take a derivative, the degree drops by 1. So when you take a look at the function that we've got right here, this is a quadratic. Okay, so I know that this is degree 2. When I take the derivative of this, I am going to get a linear function. I'm going to get a degree 1 here. Now, some things that we should notice about this. First of all, right here at the vertex, the slope of the tangent is 1. Sorry, 1. Wow. The slope of the tangent is 0. Okay, our slope here is going to be 0, which means when we sketch the derivative is going to go right at this point right here. It's going to go through the x-axis. That's where that value is going to be 0. Now, for all values, I'm going to change color here. For all values along here, okay, for all values along there, the slope of the tangent line, okay, is negative. Every one of those. But watch what happens. Way up here, let me clear up some of these. Whoops, I did not mean to do that. Let me clear up some of these things here. When you took the derivative here, notice that up here, the slope it's a negative, but it's a large negative, like negative 10. Then it becomes negative 5, negative 4, negative 3, negative 2, negative 1, and then we get 0 right there at the vertex. So when we plot that, okay, that's going to be all of the values of the derivative are going to be down here below the x-axis. Now on this other side, all of the tangent lines here are going to have positive slopes, positive 1, positive 2, positive 5, positive 10. So when we sketch that over here, as we move away from this x-intercept, the value of the derivative is going to go up. It's going to go up in a linear fashion. Okay, it's going to get positive. And so that's roughly what this is going to look like. Now, that's not exactly true. Okay, I mean, without knowing some more specific details about the parabola, I don't know exactly what the slope of that line is going to be, but that gives you a good idea. Okay, let's try again. Let's say that we start off with a cubic. Okay, and now we're going to graph the derivative of the cubic. Now, bear in mind that, again, the degree is going to drop. So if this is degree 3, we know that when we draw the derivative here, it's going to be a quadratic. Now, I know that the slope of the tangent line right here is 0, so my derivative is going to go through 0 right below that. I also know that the slope of the tangent line right here is 0. So right above that is going to be where my derivative is going to go through the x-axis. Okay, that's where it's going to take on a value of 0. Now, let's take a look at this point right here. To the left of this, what we're getting here, as we move away from this particular point, okay, all of the slopes of the tangent lines here are positive, and the further away we get a larger and larger positive value for the slope. meaning that when I try to plot that, as I move to the left away from here, the value of the derivative is going to go up in the positive direction. Now, to the right of this particular point right here, my slope gets smaller. So it's negative, gets smaller, -1, -2, -3. But it hits this kind of this minimum slope value, and then it starts to get larger again and approach 0. So what's happening in between here, okay, from here to here, is the slope drops down to some minimum value right here, okay? Then it goes back up. Shoot, sorry, I drew that badly. Try that again. Then it goes up to 0. On the other side of that little vertex right there, slope is positive and increasing, meaning that my derivative is going to be positive above the x-axis and increasing. And there's what my derivative function would look like. Okay? Now, just to illustrate really quickly how this would work if the cubic looked the other way here. Okay, let's say that my cubic did something like this instead. Now my derivative, okay, because the slope is 0 here and the slope is 0 here, my derivative is going to go through here and here, the x-axis, all along this portion right here. Okay, the slope of the tangent line are negative, but they're getting larger. They're getting closer and closer to 0 here. So like -10, -5, -2. Okay, they are actually increasing until I get to 0. Beyond that, the slopes are now positive and increasing, but then we get to this maximum value of the slope, and then the slopes start to decrease again. So way over to the left side of this graph here, my slopes are going to be negative, but increasing to 0. So negative, increasing to 0. Then in between here, the slopes increase to some sort of maximum, and then they drop down again to 0. And that's what we're seeing in the graph here. The slopes increase, and then the line sort of starts to curve the other direction, curve down again. And then when you get to the far side of this point here, now all of the tangent lines have got negative slope, and they're getting smaller and smaller. Well, you're getting larger and larger values, but they're negative, so it's getting smaller and smaller. That's a terrible drawing. But you get that idea, and that's how that would change the orientation. The orientation of the original function will affect the orientation of your derivative. Okay, so again, just keep in mind that we're talking about the slope of the tangent, and every time we do this, we're looking at a drop in degree.